One of the common questions about electrons and orbitals is about diamagnetism or paramagnetism. So how can you tell if a species is paramagnetic or not diamagnetic? Paramagnetic species will have unpaired electrons. Paramagnetic species will have unpaired electrons one or more unpaired electrons, whereas diamagnetic species will have no unpaired electrons. So if you had to tell a species, say for example vanadium 2+, if you had to find out if this was a diamagnetic or paramagnetic species, how would you do this? So first you write down electronic configuration of vanadium itself, which is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d3, 23 electrons in vanadium. So and then we figure out what is the configuration of V2+. What's the difference between vanadium neutral and vanadium 2+? When you take vanadium neutral and remove 2 electrons from neutral vanadium, you get vanadium 2+. So which electrons are you going to remove? 2 electrons. Remember, it's always the outermost electrons that are removed. So this is the first shell, this is the second shell, third shell and fourth shell. So we remove 2 electrons from the fourth shell. So what will be the configuration of vanadium 2+? 1s2, 2s2, 2p6, 3s2, 3p6, 4s0, 3d3. Now remember, it's okay to write this 4s0 as 4s0 because this will convey that you removed electrons from 4s. So now what do? You have to remember when electrons are being filled, always remember electrons are first going to the lowest energy state, lowest energy subshell, and if a subshell is available with many orbitals in a subshell with more than one orbital, I might have to cross this off. With more than one orbital, then electrons or the subshell subshell is first half filled and then pairing starts. So for the vanadium example, what happens here? The whole configuration is, again, let me write it for you again. 1s2, 2s2, 2p6, 3s2, 3p6, 4s0, 3d3. So if you keep filling these electrons So first 2 electrons go into 1s, the next 2 electrons go into 2s, the next 6 electrons go into 2p. How would they have filled up? They would have filled up like this: 1, 2, 3, 4, 5, 6. And then the next 2 will go into 3s, then again 3p. 1, 2, 3, 4, 5, 6. Of course, now the 4s is empty. It would have been like this, but right now it's empty. So these are gone. And then 3d3, there are 5 total orbitals. 1, 2, 3, 4, 5 total orbitals. There are 3 of electrons that are filled up here. So they are like this, 3 electrons. So you have totally in this species, in vanadium 2 plus, you have 3 unpaired electrons. 3 unpaired electrons. So because there are 3 unpaired electrons, this species is paramagnetic. This species is paramagnetic. Now, if this was not the case, if there were no unpaired electrons, then that species would have been diamagnetic. Now, another common question that I have been getting in the emails is about bond energies or bond enthalpies. Bond energies or bond enthalpies. Bond energies or bond enthalpies. So let's say we have a reaction that looks like this. Methane gas plus 2 water vapor yields 4 hydrogen gas and a CO2 molecule and 1 mole of CO2. When bond energies are given, okay, and bond energies are given like this. H bond energy is 436 kilojoule per mole. C double bond O bond energy 799 kilojoules per mole. CH single bond energy 414 kilojoules per mole. And OH bond energy 464 kilojoules per mole. Okay, now remember, per mole written like this or written like this doesn't matter, but this is more latest way of writing it. Okay, so these bond energies are given to us. This is the table, this is given to us. So now what is the bond, what is the delta H for this reaction? What is the delta H for this reaction when bond energies or bond enthalpies are given to us, right? Now remember, CH4 looks like this. By now we know how to draw Lewis structures, and H2O molecule looks like this, and there are 2 such molecules or 2 moles of H2O. H2 looks like this. There are 4 moles, and CO2 is like this, and there is 1 mole of CO2. Now remember what's happening. I'm going to draw it in different color, write it in different colors. These bonds are being broken. These bonds are being broken, and these bonds are being formed. This is formed and this is formed. Now remember, bonds broken and bonds formed have different signs of energy. Bonds broken. When bonds break, let me write it in a different color for you. When bonds break or breaking of bonds breaking is endothermic process. Endothermic process, meaning delta H positive or bond energy positive. Bond formation is exothermic. When bonds are formed, it's exothermic process, meaning delta H is negative. Pause this video and go back and check the bond values from the previous slide. What do we have? We have 4 CH bonds broken. 4 CH bonds broken. So 4 times 414. Maybe I should add one more step here. 4 CH bonds are broken. So summation of all the bonds broken summation of all bonds formed. What are the bonds broken? The broken bonds are 4 CH bonds and 4 OH bonds. There is one, let me show you in a different color. 1, 2, but there are 2 moles. So first bond, second bond, in the second molecule, first bond and second bond. So overall 4. And then we have 4 HH bonds that are formed and 1 and 2. So 2 C double bond O formed. Now remember, since this is exothermic, we put negative and negative for this. Right? So these are bonds broken and these are bonds formed. So now what's going to happen is we're going to say 4 times 414 plus 4 times 464 minus 4 times 436 minus 2 times 799, and this will come out to be 1.70 times 10 raised to 2 kilojoules. That will be the bond enthalpy or delta H for, not bond enthalpy, but that will be the delta H for this reaction.